Okay, so today we will start with a new discussion topic, which is among the first steps, as we all know, of the compression layout, which consists of 3 stages, as we know. The first one is transformation or prediction, which is an attempt to reduce the variance or equally the energy or equally the entropy of the source data. And then from there, we continue with the quantizer step, which may be vector quantization or whatever. That's a transformation by itself from real values or real valued vectors, matrices, etc., to indices, integer indexes. Once we have those indexes, we can now apply an entropy coding or a lossless encoder for the last stage of the compression. And today we will start with the transforms. And the transforms that we will be talking about, or the concept of transformation, is an attempt to look at the signal from another perspective, from a different perspective. That's it. It's not really a magical thing that we do when we do, for instance, the transformation of Fourier. That's the Fourier transform, for example, which is a very typical thing. It's essentially another way to represent the same signal. After the Fourier transformation, we don't have a different signal, in other words. We have the same signal, but we are representing it from a different perspective. And it very much resembles the concepts of linear algebra. So we have, for example, a two-dimensional space of, let's say, x1 and x2. So the coordinate systems are, let's say, E1 and E2, which are 1, 0 and 0, 1, the basis vectors, you may remember. And X is this point, let's say. This is the point X. A transformation is essentially another way to look at this signal, and the other way to look at it is from a different frame. For example, we can rotate these two axes by some angle. Okay, let's call these new coordinates F1 and F2, which are not 1, 0 and 0, 1, but some different things. And on this same F1 and F2 frame, the new representation of the signal, of the same signal, you see it's the same vector I'm talking about, is, let's say, y1 and y2. Whereas previously, on the axis of E1, E2, it was x1 and x2. So x was essentially x1 times 1, 0, which was one of the basis signals, plus x2 times 0, 1. And the same x can be achieved as, let me write it in red, y1 times a new basis f1 plus y2 times f2, right? F1 and f2 are the unit vectors along these directions of the red axes that we have. And it still gives you the same x. But the transformation, in a sense, from x1, x2 notation to y1, y2 notation is, it will be notated as the transform. And Fourier transform is essentially something like this too. It's not a different animal in that aspect. The problem or the difference in terms of imagination of this linear algebra concepts is that in linear algebra concepts, most of the time, the signals are just consisting of a few numbers in the form of some finite vectors, like size 2 vectors for this case, which gives you 2 dimensions. The dimensionality of general class of signals is way larger than that. It may be even infinite size. It may even be continuously varying. I have to make a pause of this recording, unfortunately, because I have to address the phone, and then we will continue. Just a minute. Okay. So we were saying that the transformation is essentially a change of basis, as long as we have the basis, of course. So in this aspect, a transformation is a different representation of the same signal using a different set of bases. And when we're talking about bases like this, then we are also talking about the linear algebra concepts of spaces, vector spaces, for example, and linear combinations, linear independence, span of the bases, dimension, etc., will become critical concepts, which are very well-known concepts from linear algebra, as we all know. But I will not go into the details of all the properties of vector spaces like commutativity and associativity, distributivity. There's an additive identity, there's a zero vector, and there's an additive inverse, the negative of the same vector, etc. They are all well-known things from linear algebra, but I will be mentioning about some more important of these linear algebra concepts, which I will start by norm, because we have to define the norm for the vector spaces of our interest, which are signals. They may be discrete time or continuous time. They may be finite support or infinite extent. So we have to know what we mean by that, by this. So I will start by the normed spaces. Normed spaces are related to vector spaces, but they will include some of the properties, but they will not include some other properties in general. This one is the space that obeys the property of definition of a norm. If we have an X, so we have an X in this normed space, then we will define a norm like this, like the linear algebra concept that we are very much familiar with. We will have these properties. First of all, the norm must be always positive, greater than or equal to 0. And the norm is equal to 0 will mean that X vector is the 0 vector. And there's no other vector that will give you a 0 norm. Only the 0 vector will give you that. The second property, if you add 2 vectors in this normed space, the norm is the norm of the summation is less than or equal to the summation of the I forgot to short circuit myself, unfortunately, otherwise it makes these glitches. The norm of X plus the norm of Y is less than or equal to this. This is also known as the triangle inequality. It's like norm of X plus norm of Y is like the edges of a triangle, and X plus Y is the hypotenuse that you can directly go to the other addition edge. And that third edge, which you may consider like a hypotenuse for the for specific kinds of triangles, is less than or equal to the summation of the other 2 sides. It's also known, this one is also known as the triangular inequality. It is one of the triangular inequalities that we have. And the norm of alpha times, alpha is a real scalar. It could also be a complex scalar. The norm of alpha times x is equal to the magnitude of alpha, or the absolute value if it is real, times the norm of x. So these three axioms must hold for a normed space. And for our case, we will be thinking of two different norms for two different types of signals. One of them is discrete, the other one is continuous. Discrete and continuous. And the discrete norm we will be defining as a lowercase l, let's say sub p. I will mention what this subscript means. And for the continuous, it's an uppercase L sub p. So these are the two norms that we will be dealing with, where p is the order. And for example, for this case, the uppercase LP, capital LP norm is something like this. It's an integral of absolute, or the magnitude, x of t, as we know, this is the continuous signal, to the power p dt, integrated from minus infinity to plus infinity, or if it has finite support, through the support, and then to the power 1 over p. It's like taking the pth power first and then the pth root. If p is equal to 2, then it means the Euclidean distance, by the way, the square distance, which is the integral of square of x of t, magnitude square of x of t, and then you take the square root of the output of the integral. But here you can generalize it to p norm, where p is between 1 and infinity. It could start from 1. If you say p is equal to 1, by the way, it corresponds to the absolute norm. If p is equal to 2, it corresponds to the square norm. If p is equal to infinity, it corresponds to the infinity norm. And infinity, 1 and 2 are the three important, as we know from vector quantization, the three important norms that we have. And if you substitute the integral with a summation, then you will come up with the summation of x of n magnitude to the power p, and altogether 1 over p. That will be the discrete version of the norm. And if p is equal to 2, that is the Euclidean for both cases, L2 norms. Okay, now these are the normed spaces. Let's put an underscore to this one, because we will have two more space types, and one will be the subset of the other, and we will be dealing with those. So the next thing is a metric space that I will mention. And the metric spaces have their own axioms, properties. The first property, for the metric spaces, we will have a distance. The metric corresponds to the distance between two vectors. So the operator will measure the distance between two vectors. And the first axiom that we have is the distance between x and y vectors is always greater than or equal to 0, whereas dxy, the distance metric, is equal to 0 means that if and only if x is precisely equal to y vector, then their distance will be, of course, 0. And the other one is the triangular inequality, is new version, the metric version of it. The distance between x and z is always less than or equal to the distance between x and y plus the distance between y and z. So now it's like traversing the triangle edges, and this distance plus this distance is greater than the hypotenuse. So it's essentially the same triangular inequality that we have, or similar in that aspect to the normed version. And the third one is, it is symmetrical. The distance between x and y must be defined to be equal to the distance between y and x. So if you come up with a formula of this D operator, which satisfies the first two but does not satisfy the third, then of course it cannot be a metric space, a proper metric space. Now, the thing which can be shown, or maybe I can ask it as an examination question for the final take-home exam. Every normed space is also a metric space. So normed spaces are a subset of metric spaces. The first one where we define particularly the norm of, the distance between x and y to be equal to the norm of x minus y. So if we are able to define the metric or the distance in the form of this norm operator, then the norm space also becomes a metric space. So we can visualize it like this. This is the normed space, and the metric space is actually a larger set. Metric space is here, because you can define the metric distance, D operator, that can be different than the norm. And the third one that I will indicate is the inner product space. And the inner product operators will be like this. That also you may remember from linear algebra, the less than or greater than signs, and in between we have two vectors. And the properties for these are x, y inner product is equal to y, x inner product except a conjugation. This is an interesting thing, because I will be talking about some inner product operator examples, like the norm operator example that I have given you for signals. So, and when I make those definitions, you will understand where this conjugation comes from. And it's very much related to the Fourier transform and inverse Fourier transforms, e to the minus j omega t and e to the plus j omega t multiplication. You will see that when you will understand that when you see it. And the second property is you can make a linear combination of x and y like this is equal to, so it's like a distributive property of the inner product operation, alpha times x and z inner product and plus beta times y and z inner product. Okay, so this z multiplication can be distributed to x plus y, or you can put the x plus y to the right hand side if you wish. You can also do that, but then the alpha and beta, if the right hand side is separated with coefficients alpha and beta must also be conjugated. Remember that, because the right hand side thing is the one that we conjugate essentially. And the third one is inner product of x with itself is always greater than or equal to 0, and inner product of x with itself is equal to 0 means that this happens if and only if this x vector is a 0 vector. Now, the final concept with respect to which is in as a subset of the other one, which is inside the other subset, is every inner product space is also a normed space. So essentially, the inner product space is the innermost space that we have, inner product. So it's the most reduced one, and the way that we can see that every inner product space is also a norm space, it actually only happens if you define the norm particularly as the inner product of x with itself, and you take the square root of it. If you define the norm like this using the inner product, then the norm space is essentially becoming an inner product space. It's a subset. So inner product space is the most restrictive form, and it is also known, if all of these are satisfied, that means if you also come up with an inner product definition, it means you come up with the proper vector space that we're talking about. For the proper vector spaces, we must be able to define the inner products, which induces the definition of the norm like this, and from the norm, we can induce the definition of the distance like this. Then we come up with the so-called vector spaces. But what is an inner product example that we have for signals? Well, for signals, we can have, for example, in L2, if you have this continuous Euclidean distance induced vector space, then x and y, these inner products, where x is x of t, y is y of t, by the way, is equal to the integral of x of t times y conjugate of t dt. So the inner product is very simple. We multiply element by element throughout the time index. We multiply the signal and then integrate. Okay, that will give you the inner product. You will notice that if y of t is the same as x of t, then this inner product will probably be large. Or if one of these are large, then the projection onto that one is also going to be large. And in little L2, for the discrete case, you just replace the integration with a summation, x of n times y conjugate of n over n. The range of n from minus infinity to infinity, or from within a distance from 0 to capital N, for example, etc. It all depends on the applications that you are doing, and those applications, when we see the examples, they will be very much obvious, but we were not aware of these things. For example, in the Fourier transform, all of these things have Fourier transform correspondence. But Fourier transform is not the only transform that we have. We will have other transformations as well. By the way, using these vector space operations, we come up with the vector space concept, which will have the commutative, associative, etc. properties, which can be very easily listed as x plus y is equal to y plus x in the form of vectors, of course, or signals in a sense, because signals also obey the vector space operations. So this is known as the commutative. They can commute, they can change their roles, their orders. The second one is the associative property. So the parentheses may associate to the first two or the last two. It doesn't really matter for the summation of the vectors. So this is equal to x plus y plus z. So it doesn't really matter where you use the parentheses as long as you're doing the summation. But of course, if you are doing the multiplication with a scalar, so this is the third, alpha times x plus y, for example, will obey the distribution rule. The multiplication will distribute along the summation. It will be alpha times x plus alpha times y. The fourth property, there exists a zero vector inside your vector space. Let's call it E space with a calligraphic E like this. It exists such that when you add to it, you will obtain x. When you add this zero vector to x, you will obtain x. It's the existence of the zero vector. And the fifth one is there exists also a negative of every x such that when you add x and this negative of x, you will obtain the zero vector. This must be inside the set. And the last one is quite trivial. There is a multiplicative identity, which is 1, where when you multiply with x, it will give you x. These are trivial axioms of vector spaces, but sometimes we need to be aware of these things. We have to remember all these vector space properties. Okay. The next topic that we have to talk about is span, which will yield us to the concept of basis. The span is a critical thing which gives us the set of all possible vectors in this vector space using a finite set of linearly independent vectors. So if you have, let's say, two vectors, let's say x1 and x2, then we can define a span of x1 and x2, which will correspond to alpha times x1 plus beta times x2 for all complex values, real or complex values of alpha and beta. And here the dimensionality will be important. What is the dimension of this span? How many different vectors can we obtain, etc. And in the vector space, if you can find the minimum set of orthogonal and unit norm, which means orthonormal vectors like E1, E2, up to En, if they are orthonormal, which means they have unit norm and they are orthogonal to each other, then these are a basis of n dimensions. Okay. Usually, we will start with the trivial or orthonormal basis corresponding to, for example, for 3 dimensions, it will be 1, 0, 0, then 0, 1, 0, then 0, 0, 1. Those 3 vectors will be the 3 trivial 3-dimensional basis vectors that we have. But using a transformation, we will come up with a rotated version of these, so that these rotated versions will still be orthogonal to one another. and they will have unit norm. And since there are three linearly independent, because they are orthonormal, three linearly independent vectors, it spans a three-dimensional space. And that will describe our transformation, just like the thing that we did in the beginning, if you may remember here. So I will rotate the basis from E1, E2 to F1, F2, and its new representation in this new frame will be Y1 and Y2. So I will define now a transformation from X1, X2 to Y1, Y2. That will be my transformation. But how are we going to extend these into the concept of signals? So up until now, all the things that we have mentioned about is for the particular purpose of making an analogy to signal spaces. And in signal spaces, we will start with this kind of representations. And in discrete time, it's the easiest. You may remember these from signals and systems courses. In discrete time, let's assume that this is our signal. Like this. At indices 1, 0, 1, 2, and here all the others are, let's say, 0, 3, 4, 5, 6, 7, 8, 9. It's a finite support discrete time signal, but it doesn't have to be. This is just an example. And let's call it x of n. So what is the value at 0? Here, the value is x of 0. Here, the value is x of 1. But it actually corresponds to a number, right? It's not x of 1 or x of 0 is not a signal. It's not a function. It's just a value. It's a number. It's like a, or it's like 5, some number. This is x of 2, etc. And meanwhile, we have a mother basis from which we generate automatically the other basis signals. And that is the unit sample or unit impulse. As we know, it's delta of n. At 0, its value is 1. The other basis signals, this is one basis signal. The other basis signals can be generated from this one by simply shifting it, like delta n minus k. Delta n minus k is another unit sample at the position n is equal to k. For example, when n is equal to 4, this is delta n minus 4 at 4. Its value is again 1. Now we have these separate signals, which we will consider as basis signals for our representation of our signal. And now, are they a basis signal is the question. And to answer that question, we must find a construction formula as a summation of these basis signals. So what are those basis signals? They are delta n minus k. And I have to multiply them with some scales because I will linearly combine them. Let me call them a sub k. For every impulse, I have a corresponding scale. And when I combine them, for all k, I'm expecting to come up with my signal, which is my x vector. So how can we do that? Is it possible to do it? And the answer is very trivially, yes, it is possible, because these AKs are essentially x of k's. Because when you multiply this sample, for example, when k is equal to 0, delta n minus k is equal to delta n. This impulse times this value will give me this sample impulse with the correct magnitude. For delta n minus 1, which is an impulse or a sample here, if I multiply it with x1, then it will become a taller one, as tall as this one, plus x2 times a sample here will give you this longer sample, plus this sample, plus this sample, plus this sample. When you sum them up over all possible case, we are going to obtain the representation. So I will write it in the correct form as we know. X of n is actually k from minus infinity to infinity xk times delta n minus k, which is a formula that we know from signals and systems with the name convolution sum. The name of this formula was convolution sum. It's not convolution, it's convolution sum, or you may think of it like the convolution of x of n and delta of n. I'm convolving with an impulse which will give me the same thing. But right now, the concept will be split into the basis representation, where these are the bases and these are the scales, and I'm combining. So this is making a combined scaled basis. So it's something like having x1 and x2 to be equal to x1 times 1, 0 plus x2 times 0, 1. So instead of saying it as x1, x2, or instead of saying it as x of n, I'm writing it as x of 0 times delta of n, which is the delta of n is the first basis vector, and x of 0 is the first element that we have, plus the second element times the second basis, etc. That's a basis expansion that I'm making. And this original basis representation is known as the time basis. Without the basis, you cannot really represent the signal. You cannot say, you can only say x signal, but if you say x of n, you immediately mean that you are using the time basis, which are the impulses. And if you alter this basis delta n minus k, if you drop them, and instead of it, you use a different orthonormal set of functions, if you substitute them, then, of course, these scales will change. X of k will change, or it may be something else. So this new representation will be different from x of n. Here, x of n and x of k are the same value-wise. This will be a new representation, and this new representation will define the transformation from x to the transform domain. Again, I will scroll up. That's a similar situation as, instead of 1, 0, if I use the F1 basis, and instead of 0, 1, I use the F2 basis, and they must obey the basis properties, which means these two must be orthogonal to one another. So, how do we define orthogonality? By saying that the inner product of F1 and F2 will give you 0. And they must have unit norm. How do we define norm? By the norm space properties, which is the inner product of F1 with itself, taking the square root, will give you the norm of F1. It must be equal to 1. For F2, it must also be equal to 1. If you can find such two different bases, then from x1 and x2 to y1 and y2, you will have a transformation. That's what a transform is. But of course, for those, the basis must be, it must be a basis. The basis must be a basis, which means it must satisfy two properties. So basis must satisfy, let's call these bases as phi sub k of n. For this one, it is delta n minus k. Phi sub k of n is delta n minus k for our case, for our example. They must have two properties. The norm of phi k of n must be equal to 1. They must have unit norm. How did we define norm? We will remember. And the second property is inner product of phi k of n and phi, let's say, L of n must be equal to 0 if k is different than L. So two separate basis vectors must have 0 inner product with each other, which is the orthogonality principle. And for the first one, we will use the Euclidean norm property. We will say it like summation for all n, oops, excuse me, phi k of n square. After that, you take the square root, but the square root is not important because if the square root is equal to 1, then the square itself is also equal to 1. This must be equal to 1. And this is for the first. And for the second, this is for the first. For the second, we will define again the inner product in the form of this. We will say phi sub k of n times phi sub L conjugate of n. This summation must give you 0 if k is different than L. Now let's go back to our example of phi k of n is equal to delta n minus k case, this case. Is this or are these orthonormal? And the answer is yes, they are orthonormal because they have unit norm, first of all. What's the norm of this example? Phi sub k of n is equal to delta n minus k. So what is the norm? What is the norm of delta n minus k? It's the square root of the summation of all the samples squared, which are all zeros, 0, 0, 0, 0, except for one case, it is 1. The others are also 0. And it's 1 at n is equal to k. So when you sum them up, it's infinitely many zeros plus 1 will give you 1. So this will be equal to 1, which means that the norm of the impulse is 1. And then are they orthogonal? For that, we have to look at this delta n minus k, which is phi k of n, that is non-zero at n is equal to k. And we will choose another one. Let's say here. This is L. It's 1 at L, where L is not equal to k. Okay, k and L are different. And then we term by term multiply them. In fact, we have to multiply with the conjugate of the second one, but they are all real here, so it doesn't really matter. We are multiplying 0 with 0, 0 with 0, 0 with 0, and then 1 with 0, and then 0 with 0, and then 0 with 1, and then 0 with 0, etc. So the summation will give you 0. the multiplications are all 0. The summation of all these zeros are summation of zeros, which will be equal to 0, telling me that delta n minus k is orthogonal to delta n minus L. I'm pretty aware that these are awkward notations or explanations, because we know things from linear algebra. When we say orthogonal, we are talking about this. So there's a 90 degrees in between the two vectors, but these are signals. So we don't really draw the signals and show that they have 90 degrees in between. In fact, what we do is we define an inner product formula, which is given to us as multiplication of the first with the conjugate of the second one, and summation through all of its items, term by term multiplication, and then summation. That is the definition of inner product. And using that inner product, if the inner product gives you 0, we say that these two are orthogonal. Okay, that's the definition that we are going to use. And clearly, the time basis of delta, the impulse function, is an orthogonal set of bases. But do we have other set of bases? And how can we further analyze these coefficients? Let me go back a little bit. I said before that these AKs from convolution sum from signals and systems, we know that these AKs are essentially XKs. They are equal to X of K. But I didn't show you the systematic way of obtaining these AKs using linear algebra concepts. For that, I will scroll up a little bit and show you something. Yeah, to the first example. For example, we know that x, which is x1, x2, is equal to x1 times 1, 0 plus x2 times 0, 1, right? Suppose that you know 1, 0 and 0, 1, but you don't know what is x1 and what is x2, a hypothetical case. How do you really determine this x1? You determine x1 actually by projecting, making an inner product of this x vector to the E1, to the 1, 0 vector, making this projection. When you make this projection, it gives you x1. So that's how you define x1. Actually, therefore, x1 is equal to x inner product E1, isn't it? That's how we find it. And similarly, x2 is equal to x inner product E2. Sorry. The same is valid for y1 and y2 too. y1 is equal to x inner product f1, and y2 is equal to x inner product f2. As simple as that. They're just inner products. These scalars can be obtained as inner products. Now I will scroll back and see if it works for our example too. So I said that AK is equal to XK, but actually it must be equal to X of N inner product delta N minus K, the basis. This is the signal. This is the basis. So taking the inner product of signal and basis, it will give me the coefficient AK. And if you take the inner product of maybe I should draw it again like this. We have a signal like this. And so let's say that this is K. This point is K on the N axis. So this is X of N. And now I have 1 and others to be equal to 0 at K, K plus 1, K plus 2, K minus 1, K minus 2, etc. All other sample points. This is delta N minus K. So how do I take the inner product of this and this. What was the inner product formula? The inner product formula was term-by-term multiplication first, and then summation of the results. So let me term-by-term multiply. This value is multiplied by 0. This value is multiplied by 0. This is multiplied by 0. This is multiplied by 0. So they give me nothing. And then this value, which is, by the way, x of k, that is the value, is multiplied by 1. And the others are also multiplied by zeros. And when I sum them up, it is 0 plus 0 plus 0 plus 0 plus xk times 1 plus 0 plus 0 plus 0, etc. So the inner product of x of n and delta n minus k will give me x of k, which is a confirmation of what we already have, right? We already said that this ak, as we know, must be equal to xk. Even if you don't know it, you can just simply construct the formula as this thing, this value scale is equal to the inner product of x and the bases. That's how you do it. You take the inner product of this and this, according to the inner product formula, of course. If it is continuous, if these are continuous signals, then you must use the term-by-term multiplication, and then you integrate. You don't sum up, but you have to use the integral. And that is precisely what I would do, but we're running out of time already because of the delay that I caused. So we can stop at this point. We will continue from here, and the concept of transformation will give you a totally different perspective of looking at, for example, the Fourier transform and all other transforms. And you will understand that essentially a transformation is the representation of the same signal from a different basis perspective. And guess what? Using for the Fourier transform, we will not be using delta t minus tau or n minus k, etc., but we will be using e to the j omega t, where omega is like the k, the different parameter will be the frequency, and are they orthogonal to one another, etc., will be of concern, of course. But even Fourier transform will obey these rules. So I think it's time for me to stop at this point. If you have any questions, you can ask. Otherwise, we will continue next week. So, any questions?
No, I don't.
All right. That's fine then. So I'm ending the meeting. See you next week, hopefully. Goodbye.